any visual feedback. All right. Before I continue, to justify my life, I have to give a short paid advertisement. I'm at Oak Ridge. We have neutron sources. They're open to the world. And you can find out how to apply for time at this website. So let me continue. Potassium copper trifluoride is something that I was stunned to realize I've been working on now for over 30 years with a great variety of experimental collaborators listed here. But in particular, I'd like to call out two people, Alan Tennant, who's been there from the beginning, and Alan Shea, who's a postdoc who has really done a lot of the work that I'm going to show when I get to the new part of the talk. So my outline has a mnemonic so I can remember where I'm going. It's something old, something new, something borrowed, something blue. Right? The blue is the crystal. Old is I will talk a little bit about the spin 1/2 antiferromagnetic Heisenberg chain. Something new is I will talk about neutron scattering and what we can say about quantum Fisher information and entanglement. And the borrowed is the KPZ dynamics, okay, Kardar-Parisi Jang. So let me just show, first of all, some papers that one can look up for details. Since this is recorded, I won't read anything through them. Let me begin with something old. So the spin 1/2 Heisenberg antiferromagnetic chain. We are approaching the 100th anniversary of the Heisenberg model in a few years' time, interestingly enough. So this problem has been around since 1928. And the ground state for the spin 1/2 Heisenberg antiferromagnetic chain, defined by this Hamiltonian, was solved by Hans Bethe in 1931. This was the problem for which he introduced the now famous Bethe-Ansatz. The ground state was pretty complicated in terms of working out matrix elements and so on. And actually, there was very little progress understanding the excited states for about 30 years, where the low-lying excited states were worked out by Descloseaux and Pearson. And even then, to work out things that were measurable, like dynamical response functions, was very hard. Some progress was made by Muller and collaborators in 1981 with approximate solutions based on some rules and so on. But in that same year, Fadiev and Takhtajan published an important paper that changed our ideas about excitations in this system, which I will come to. And this led to some further work by Haldane, which I think everybody is probably familiar with or has heard about. And even more recently, there's been some renewed theoretical interest in the hydrodynamics at long wavelengths, work by Thomas Prosen and Joel Moore and their collaborators, which I will touch on at the end of this talk. And I think Joel Moore will give a lot more detail in his talk tomorrow. So this Heisenberg antiferromagnetic chain ground state is a singlet. The excitations in linear spin wave theory have a sinusoidal dispersion. And here pi odd is an antiferromagnetic point. Pi even would be a nuclear point. The Descloseaux-Pearson spectrum that was worked out for the low-lying excited states actually also had a sinusoidal dispersion, but was renormalized from linear spin wave theory. And experimentally, this was, I'll say, verified in quotation marks by experiments done in the 1970s by Yasu Endo and collaborators like Bob Bergeneau and Gen Shirani, showing that if I took the exchange constant as measured with spin 1/2 expressions, that the dispersion of the observed low-lying excitations indeed fell along this Descloseaux-Pearson line. Now, there was actually something a little odd about this in that if I tried to fit other measured quantities to a classical expression, I could get a self-consistent fit between the J that described those quantities and the one that also described the dispersion of, say, a spin wave. So the quantum effect was thought to be, in a sense, only a renormalization. But of course, there was a lot more going on. Now, what we learned from Fadiev and Takhtajan was that the actual natural excitations out of the singlet ground state really have a spin 1/2 relative to the ground state. So they are, in fact, spinons. And if I try to look at a measurable quantity, I create these in pairs. I have matrix elements for pairs or even numbers of spinons. So the physically observed states, if I'm looking at an excitation out of a singlet ground state, actually have a total spin of 1. Now, if the underlying spin in the model is an integer, the spinons are actually bound. It's like a quark-antiquark pair in a meson. And there's an energy gap, the Haldane gap, which is like the rest mass of the meson. If the underlying spin is half-odd integer, which includes spin 1/2, the spinons are, in some sense, they're asymptotically free. So one consequence of that is that for the spin 1 chain, the spectrum is got a well-defined excitation with an energy gap. For the spin 1/2 chain, the spectrum actually is a continuum with a very broad response in energy around the antiferromagnetic points and narrow around the so-called nuclear points. And this is because with two particles that are free, there are many ways to conserve energy and momentum. Okay. So potassium copper trifluoride is a good example of a material that behaves very much as if it were a quasi one-dimensional or a one-dimensional spin 1/2 Heisenberg antiferromagnetic chain. It's an almost cubic system that is slightly tetragonal. It's got chains of copper 2+ ions running along the C axis. And because of orbital order, you can see there are sort of 180-degree overlapping bonds going in the C direction, 90-degree bonds in the A and B direction. And it's got strong antiferromagnetic interactions along C, weak ferromagnetic interactions along A. The system, of course, with some kind of ferromagnetic interaction does order around 40 Kelvin or so. But as we'll see, it retains a lot of the features of the underlying Heisenberg spin chain, including the spin 1/2 or spin-on fractional excitations. So this is also a little bit of a trip on how much our equipment has advanced in the past 30 years. We looked at this material in the early 1990s at ICIS using the chopper spectrometer known as MARI. And at the time, the best you could do was sort of integrate over this small array of detectors. And what I see here is the cut of this detector array through Q and omega space, where I have momentum Q vertical, omega energy horizontal. This is the spectrum. And whenever I cut through the spectrum, I plot here as a function of energy the response, and there you see it. And the red line is an independently measured non-magnetic background. The dark solid line was this estimate of Müller et al. For the response function for the spin 1/2 Heisenberg chain. And actually, this was really a couple of things. It was the first verification that one really clearly had this line shape and sort of energy up here representing the spin-on continuum. And it was also one of the first successful applications of a chopper spectrometer to a material that wasn't completely isotropic, because in the old days, it was believed that they would not be useful for that. Now, following that up, if we looked at the temperature dependence of the scattering here, you could compare it to predictions from field theory for the behavior of, if you like, a spin-on gas. That is the solid line, and that can be contrasted with what one expected for temperature dependence of classical excitations. And it's pretty clear this thing's temperature dependence behave as you would expect for spin-ons. Now, as I mentioned, the chains are actually in reality coupled, and that changes the low energy dynamics. So I'm looking here around this Q equals pi, which is 0, 0, minus 3/2 in this experimental system. And the response function for a pure 1D chain looks like this spin-on continuum. If I had spin wave theory and took it to a large order, I see a continuum coming from 2 magnon scattering. But in fact, this spin total 1 excitation, of course, it breaks up into 3, and what really happens in a set of coupled chains is I get 2 transverse modes, which are basically spin waves in the ordered state. I have a longitudinal mode at a somewhat higher energy that's characteristic of the interchain coupling, and above that at high energy, I get the continuum. So in those days, we called it a longitudinal mode. These days, it's fashionable to call it a Higgs mode. Here you can see some actual data. This is the longitudinal mode. And we had to do a fair bit of work to prove beyond the shadow of a doubt that it was longitudinal. If I make a plot of intensity going vertically in this direction, and I look as a function of temperature, I can see this lump of scattering when I'm down below 40 Kelvin at the ordering temperature. And here I see the continuum, which I expect when I'm disordered at high temperature. Similarly, if I look in this case at 10 millivolts and cut horizontally as a function of wave vector, I see here at low temperature, these are the transverse spin waves. At high temperature, this fills in. And one can arrange to do an experiment using polarized neutrons, which it turns out, I won't go through all the details because it will take a bit of time, but we can set things up so that what we call spin flip scattering comes from purely longitudinal excitations. And you can see here a result of a measurement at that same wave vector. And at 6 Kelvin, I've got a lump of scattering that corresponds to this longitudinal mode or Higgs mode. And when I go to high temperature, that's gone, and I come back to the continuum. So moving along from 1990 to the early 2000s, new instruments were built, and now we could just measure the spectrum in an extended zone scheme, and it looks like this. Now we make color plots, which are beautiful. Of course, they don't convey as much quantitative information. They just look good. But at some level, you can see this nice, if you like, spin-on continuum very clearly. And in fact, this data was of high enough quality that we've been able to analyze it in great detail. Now, one thing that comes out, if I had the pure spin 1/2 chain, basically it is quantum critical. And if I add in any interchain coupling, of course it orders. Without interchain coupling, it doesn't. But being quantum critical, it should exhibit at that Q equals pi E/T scaling. And in fact, one can see this and you can identify the region where it's clearly visible. So here's a sort of energy versus temperature diagram. In the ordered regime, this corresponds to the 3D nonlinear sigma model, where I might see the Higgs mode or other behavior. We call it a crossover region. But depending on where you are in energy and temperature, this thing looks purely like a 1D Ledinger liquid in the critical state, and it exhibits this E/T scaling. So you can get a lot of information out about that. And as the ability to calculate theoretical response functions improved with sort of DMRG based on the beta ansatz, we could do a much more quantitative comparison with the experiments. And basically, what you see here is sort of a typical measurement at 150 Kelvin compared to time-dependent DMRG. And I can compare this now to the Ledinger liquid field theory that I showed before, and you can see that where that misses a little bit of the detail of the experimental measurement, this DMRG really gets it very well. And the point is, we understand the model, we understand how to calculate response functions, and now we're going to use it for something new or something sort of new-ish, which is looking at entanglement with neutron scattering. Okay, so here's the basic problem. If I have a solid state system, how do I see if I actually have quantum entanglement? How do I measure it? Right? There are things like entanglement entropy that can be useful for finite systems, but for an extended solid system, we don't really have a good measure, or at least it's difficult. And on the other hand, entanglement is now recognized as something that we ought to think about, certainly important for quantum information, and it's significant in various problems of contemporary interest, right? We don't really have, in essence, a sort of single silver bullet way of measuring this. Now, the traditional way of approaching any sort of problem in quantum magnetism where I measure a response function is I compare the data to a theory of some sort. So here's a recent example, sort of picked almost out of the air, of a pyrochlore, where you see some data on the left. And, you know, here's linear spin wave theory, which is one model. Here's molecular dynamics, which is another. This isn't necessarily a quantum entangled system. I can get a good feeling for it. But sometimes it's difficult to get a good model for some arbitrary, highly entangled state. So what we're looking for here are various model-independent approaches, and we're trying to see how well they work in this system where we actually from years of study, have a good idea what's going on. So the basic idea is we take entanglement witnesses, we apply them to neutron scattering data, and we see how entanglement comes out. But we do this actually both for the experiment and see if we measure entanglement, and we can also do it in this case for a theoretical model and compare them, right? So then we cross-check and we see if these entanglement witnesses work. Now, I should say an entanglement witness, it's an experimentally measurable quantity that gives you some idea of entanglement, but there's not necessarily one size fits all. The same way there's not one order parameter fits all for all phase transitions, right? So one has to think about the physics at hand. So what are they? Well, they're observable quantities related to entanglement in some fashion. What is entanglement? Well, I can describe it easily. If I have a pair of spins in some total quantum state, they're entangled if I have off-diagonal, non-vanishing off-diagonal terms in a density matrix, right? So the problem with that is it's hard to directly measure these off-diagonal terms in a density matrix, get those matrix elements out. So we have to find other quantities that are somehow coupled to it. So here we're going to look at 3 specific entanglement witnesses and apply it to this data from KCuF3. And these are the so-called one-tangle, the two-tangle, and then quantum Fisher information. Okay, so neutron scattering measures this correlation function, which is in turn proportional to the imaginary part of the dynamical susceptibility. Okay, so in principle, if there's entanglement, this will be contained in this magnetic structure factor in the dynamic susceptibility, but we don't always know exactly how to find it. So that's why we're looking for sort of model independent quantities that we can measure and see where they'll be useful. So the first one is basically this one-tangle. It's only useful at 0 temperature, and it quantifies the 0 temperature entanglement of a spin with the rest of the system. I've written down this expression, which really applies specifically to the spin 1/2 case. And you'll notice if I had a magnetically ordered system with the full moment ordered, that would be ordered along one axis, right? And so this M alpha quantity is a quarter, and this is defined as 0, right? So it would be 0 for a fully ordered system, non-zero if the spins are fluctuating. This tells me something about how much the spins are fluctuating at 0 temperature, a very simple measure. Okay, it doesn't tell you anything about the type of entanglement you have. So if I have an isolated dimer, that will have a one-tangle of the maximal value of 1, right? And I can't necessarily determine just from that whether the system has some other kind of order, right? Or entanglement between multiple dimers. Okay, then there's what we call the two-tangle, which is a measure of bipartite entanglement of a spin with its neighbors. Two-tangle is related to the concurrence. The concurrence, which is defined here, is basically a measure of the entanglement of 2 spins separated by a distance r. Again, this is an expression specialized to spin 1/2. And you know, this requires us to know this spin real space correlation function. This is also, I should say, specialized to isotropic systems. And the two tangles a sum over that. Basically, this is measuring how much this correlation exceeds the classical limit of plus or minus a quarter, if you like, right? So if I have, you know, s plus 1 compared to a quarter, obviously in the quantum limit, that's different. But if I have an anisotropic system, the definition gets somewhat complicated. It requires a calculation of the real space correlation. And this isn't always applicable to any entangled system. For example, the KCuF quantum spin liquid, which was discussed yesterday, basically has a two-tangle of 0, even though everybody would agree it's highly quantum entangled, right? So then the last measure is the quantum Fisher information, which actually for spin systems can be written down here. Q here actually just refers to quantum, although this is measured at a particular choice of wave vector. It's not integrated over all wave vectors. The natural wave vector here being Q equals pi. Now this gives a lower bound on entanglement. And if I measure the cross-section in absolute units, it turns out that if I have this normalized quantum Fisher information defined as such, right? If I have QFI and QFI greater than M, the system must have at least M+1 partite entanglement. Okay. So basically this comes from the variance of the observable quantity, right? And I guess you can read up in these papers the fact that it actually has a lower bound depending on the number of particles involved, which can be inverted. So if I measure the information, I can get a bound on the number of entangled particles. Okay. So, and it was shown by Hoek et al. A number of years ago that for a spin system, I can actually experimentally measure this in principle using this integral. So let's see what happens if I look at KCuF3. Basically, as I said, I'm going to take experimental data, compare it to simulated data, see whether it makes sense. Okay, so obviously the system is well characterized, which I've mentioned before. We have DMRG calculations that we can compare it to. We also have sort of beta ansatz at 0 temperature. And you can see here data compared to the calculations. It's very well characterized, right? So here's what we find from the one-tangle. At low temperature, the ordered moment is about half a Bohr magneton, right? Compared to the 1 Bohr magneton that you expect for spin 1/2. So if you like, that's kind of like spin around a quarter. So the one-tangle turns out to be about 3/4. Theoretically, if I had the true spin 1/2 Heisenberg antiferromagnetic chain, there would be no order whatsoever, and this would be 1. But this tells us something about how much fluctuation there is in the spins, even in the ordered state. So what happens if I measure the two-tangle? Well, measuring the two-tangle turns out to be tricky. And the reason it's tricky is we have to extract the pure magnetic scattering in order to do it. And a lot of the pure magnetic scattering, or the large contribution, comes near zero energy. Zero energy has two problems. One is we have acoustic phonons around, especially as we raise the temperature. The other one is we have in neutron scattering this annoying incoherent scattering that is also non-magnetic. So if I just naively go ahead, measure the experiment, compare it to DMRG, I find that it sort of looks like it, but the two-tangle calculated by DMRG is way off. The way to get around this, now in the experiment, one has to exclude the low energy region. So if I exclude the low energy region from DMRG, it looks like this, which is actually a little more reasonable, right? So I do have some ability to look at this two-tangle and say, well, yeah, this has probably got some sort of bipartite entanglement based on a two-tangle. But where this really kind of shines is where I go right ahead and measure the quantum information, the quantum Fisher information. Now, I will point out that that 10th function actually vanishes for omega going to 0. So the issue of not properly weighting the low energy scattering actually pretty much goes away if I just work out the quantum Fisher information experimentally. So now I can compare it directly to DMRG. Now there's both the experiment and DMRG in some sense, they have a non-zero resolution, and that actually shifts the quantum information a little bit. But you can see here, even by DMRG, we get a quantum Fisher information at low temperature, a little bit under 2, which means that this thing has to be at least bipartite entangled and possibly more. Beta ansatz with no experimental broadening, or even with a bit of experimental broadening artificially inserted, would tell you that it has to be at least 3-part entangled. And this persists actually up till about 75 Kelvin or so on for the KCuF3 data. So indeed, we see that there is at least two-part and probably three-part entanglement in the system. And basically, this shows it's promising to apply this quantum Fisher information method to extract entanglement from other systems or get some idea of it where we may not have a model to compare to. Right? It actually works pretty well here if one is careful about things. So here's the sort of ultimate meaning of the results. The one-tangle shows that there is an entangled ground state. There's a lot of quantum fluctuations, if you like. The two-tangle in this case does show entanglement, but it's sort of prone to experimental artifacts. And as I mentioned before, it's not totally reliable for all systems. On the other hand, the quantum Fisher information, which is sort of model independent, looks like it might actually be a useful probe for other materials to sort of say, yes, the ground state or the system has a lot of entanglement, or no, it doesn't. Okay, so let me now come to something borrowed, which is the Kardar-Parisi-Zhang KPZ dynamics and how it applies to the spin 1/2 Heisenberg antiferromagnetic chain. So Kardar-Parisi-Zhang is a mouthful. Actually, if you look it up, it's one of Parisi's more cited papers, interestingly enough, not what he won the Nobel Prize for, but it is highly cited. So why does this come up? Well, for the last decade, there's actually been a lot of theoretical activity trying to understand sort of high temperature collective behavior of these spinons. And in particular, Joel Moore and his collaborators have done a lot of work on this, and also Thomas Projan. And the bottom line is there are some actually surprising results that have come out just recently. So this KPZ theory actually was a classical theory that described the growth of interfaces, right? It was published back in 1986 and basically shows this equation for the growth of interfaces, which includes some diffusion, lateral growth, and some noise. Okay, and it's been applied in all kinds of situations for different classical models, everything from traffic flow to Tetris to burning paper, coffee stains, etc. So it's a model that's well established. Naively, one wouldn't think it had much to do with the Heisenberg antiferromagnetic chain, but it turns out that actually it does have something to do with it. If you look, in this case, not in the region where we spent almost 30 years studying where the spinons are, but down here near Q equals 0 and at very low energies where we have practically no signal. And what Joel Moore and collaborators showed was that if I look at this carefully and I look at how the intensity at energy going to 0 depends on Q right in this neighborhood, there's an exponent from which I can extract more or less the form of, if you like, the hydrodynamics of these spinons. Okay, so if it goes like Q to the -2, that's kind of standard diffusion. If it goes like Q to the -1, that's ballistic transport. And somewhere in the middle is the prediction of KPZ, which is we sort of call super diffusion. So this is something that we would not have dared to measure with the previous generations of equipment because, as I said, the signal here is vanishingly weak compared to the signal from the regular spinons. But again, we have next generation spectrometers. This is the Sequoia spectrometer at the spallation neutron source at ORNL. And this allowed us to make measurements now of this regime down near Q equals 0. So just to remind you of the sort of natural energy scale of this thing, the top of the Becquerel-Pearson part, which would be normally like a sort of spin wave zone boundary energy, is about 55 millivolts. And the top of the continuum, if you like, is around 100 millivolts. So we're looking down carefully in this neighborhood. And the upshot is, after doing some analysis, the exponent is approximately 1.5, certainly much closer to that than it is to either 1 or 2, which tells us that somewhat surprisingly, at least from the point of view of an experimentalist who's looked at this for a while, these KPZ dynamics that were meant to describe classically growing interfaces actually also describe the hydrodynamics of, if you like, spinons at high temperature in this limit. Okay, so they have a super diffusive hydrodynamics, and which has been characterized as a strange sort of fluid behavior. And I guess, as I mentioned, you'll hear a lot more about the significance of this from Joel Moore tomorrow. And since I can't see the time, I'll just mention that we still have a lot to learn about this. We have, the data is published if people want to look at it. It sort of verifies the hypothesis that's come out in the past few years about spin-on transport. Surprising that it actually applies in this quantum system. And it's also surprising in a sense that you can find out something about transport properties, this limit from neutron scattering. So thank you for your attention. And I don't know if I've tried to leave enough time for a few questions and for lunch. Hopefully we're there, because I don't see the time.
Yeah, you've done a great job, Stephen. Thank you very much for a great talk, including a historical overview and everything else. Let me just nucleate questions by asking you, what is Heisenberg reading in that picture you have there? Looks like he's looking at his cell phone, but he can't be.
I'm pretty sure it's not a cell phone, but maybe it was his little black book. I don't know.
It's beta, not Heisenberg, right?
It's
Yes,
beta.
it is beta,
It's
right.
beta. Okay, it's beta. Okay.
Yes.
Okay.
Looking at the notes for his ansatz, perhaps.
Yeah. Okay, questions to Steve. People think this
I have a
through.
question. So you mentioned all these measures of entanglement.
Yes.
Basically, this is the statement that unless there is entanglement, these quantities will have a different magnitude, or is that the statement? In what sense?
Okay, we have to be careful, because you can measure these quantities, and under some they don't all apply under all circumstances. So, for example, the 2-tangle is 0 for the KCuF quantum spin liquid, right? Which is an exactly solvable model.
No, that's a separate issue. No, I'm asking the question the other way around. If these quantities are non-zero, they tell you you have a certain type of entanglement.
Yes. So for example, the quantum Fisher information, if I make a measurement in absolute units and I define that normalized, let's see if I got it here. Okay. I guess I thought I wrote down the normalized form of it somewhere. There we go. All right, so if I have this quantity here, right, if it turns out to be greater than m, I have at least m plus 1 partite entanglement, if you like. Right, so if that number is greater than 1, I have at least bipartite entanglement.
What does m plus 1 partite entanglement mean?
It means that whatever okay, if I have m partite entanglement, it means that in the ground state, you always have at least m spins that are entangled together, right? So if I have bipartite entanglement, it tells me that whatever the state is, there are at least always pairs of spins that are entangled in the ground state. If I have 3-part, it tells me that however I write the ground state, I always have at least 3 spins entangled with each other. Right.
And you're working at finite temperature, so it's not a statement about the ground state, right? Are you saying the state, the thermal state is made up of states that have entanglement in them?
Okay, well, so ground state might not be the right way to say it, but if I look at the let's say the configuration at that point, right? So what this tells me is if the ground state is, the ground state obviously will have the most entanglement, one would think, at t equals 0, right? As I warm it up, it's losing coherence, but it's still statistically, at least, it's maintaining that amount of quantum entanglement in the state that's dominating that response.
And it's independent of classical correlations. Is that right?
Independent. Well,
I mean,
it's not I'm not sure whether
over
I
and
can
above.
absolutely make that statement, but this is not dependent on a model. Okay, it's just a quantity I can extract if I have a measurement of the response function. So the classical correlations will also be there. I mean, basically, if I'm looking at the concurrence, for example, that's related to what I would have called a classical correlation. But this is something somewhat different, right? It's more related to a variance in the measured quantity.
Okay, Parmesh.
Hi. In your measurements, have you taken these boundary effects into consideration?
Sorry,
Especially the boundary effects, like taking the spin chain with on a finite line segment with open boundaries, let's say.
We haven't done a correction for that, but the point of that is that if you look at our spatial resolution, if you like, right, which corresponds to the minimum wave vector we can measure, that's really the limit on the extent of things. And so the system itself is larger than that.
Right.
So sorry, I was going to say that's the point of trying to come up with a measurement in a sense that applies to an extended system.
Okay. Also, my internet was kind of unstable, so I couldn't really follow all the slides. But somewhere I saw that you mentioned some 3/4, and then you said you would expect a spin 1 instead from the Beath ansatz.
Well, okay, I'm not sure what that was. I do know where I mentioned 3/4 was probably just on this slide where I said,
okay,
for spin 1/2, SS plus 1 would be 3/4. The way I've written this is only true for spin 1/2. The concurrence would be written differently for different spins, right? I mean, this is not the general, if you like, expression, but it simplifies in the spin 1/2 case to this.
I think he might be referring to the measurement of the one-tangle. That was like 0.75 as opposed to 1.
Ah, okay.
Right, yeah.
So this also is the specialized to spin 1/2 expression. And so I guess what I believe I said is if I had a system that was, say, completely ordered, right, then what I will have for spin 1/2 is one of these components will be 1/2 and the other two will be 0 if I choose the quantization axis in the direction of order, right? This is for a single spin, so then this thing goes to 0. And what I mentioned was, well, I think that's all I really said about it.
Okay. Hans,
Thank you.
You have a question, Hans Henning.
Yeah, thank you. Yeah, very nice talk. So since you talked about the spin 1/2 Heisenberg chain, so as you mentioned, that has a critical field at high fields. So when you go from the Luttinger liquid to the polarized state, so I mean, can you calculate like these entanglement measurements all through the field range, and for example, see what happens when you go from this quantum entangled state to the classical magnon?
Okay, well, I didn't actually mention field dependence in this talk.
No, yes.
But in principle, you should be able to apply such a measure after making measurement with a field and see what that does. I mean, obviously, if you go to a fully polarized state, right, that's equivalent in some sense to an ordered state. So, effectively, you don't have quantum entanglement in the state that's described. So you should be able to follow that in principle. And we have not done that experimentally, but it's probably something that should be tried. I mean, what we're hoping to do is apply this to other systems where we don't have necessarily a model that we can just refer to, and hoping that it's a useful exercise. In some cases, I think it will be.
Thanks.
Okay, great. Tim Reeder, you have a question.
Yeah, I might be repeating a question here, but the one-tangle, I think, is a measurement of just the spin fluctuation at a single
Pretty
site.
much, yes. Yes, effectively, yes.
And you're at above the ordering temperature, which is like 40 Kelvin.
No, the one tangle is only really defined at T = 0.
Sorry, I'm referring to the, I think for your copper, or yeah, for the compound, you pulled out a number from the spectrum of like 0.76 or something like that later in the talk.
Right, right. Well, that's the tangle. So the reason where that comes from is the following. You can measure the size of the ordered moment in the ground state, right? So that can be measured at 4 Kelvin or 2 Kelvin or whatever, which is not T = 0, but we're applying a T = 0 theory to it. So it turns out for this material, the ordered moment is about half a Bohr magneton, which if you like, if I translate that into the equivalent spin, that's spin of a quarter, right?
Okay.
Spin a half would be 1 Bohr magneton. So if I look at this formula, right, two of the alphas are 0 because it's collinearly ordered, but it's only applying to one spin anyhow. So I take off 1 minus the square of a half. So that's where I get about 3/4. So that's the number one gets out of the one tangle.
And then I had just a little quick question. In the introduction part, you mentioned like these improved modeling with once you involve the Hans-Bethe ansatz.
Right.
I was curious, there's two different Hans-Bethe. There's oh yeah, that one. There's all spin-on and two spin-on. What's the difference between those?
Okay, so this was well, there's an approach to this where, qualitatively, I haven't drawn this little cartoon, but if I imagine that I just have a nail state there, right, sitting on here, and I flip one spin, right, and then I flip a couple spins beside that one spin, and then I flip a few more beside that. Then what I have are two nail states that are separated by walls, okay? So in a sense, if I'm in the Ising limit, that kink at each wall is basically roughly equivalent to a spin-on. Now, what we call a spin-on is actually more complicated than that because it's a combination of some even number of walls, and Wannier state or whatever. But I can do an approximation to this where different people define it differently, right? Where the two spin-on could mean I just include states with two walls and add those together, or I have states that are dominated by the two walls. So that's an approximate eigenstate that can be constructed. And it turns out that most of the measured intensity can be described just by those two spin-ons. But so that was, you can look in the literature and you can find people have done two spin-on calculations, but J.S. Coe and others have basically found a way to, I don't know if sum the series is the right way to describe it, but they've managed to find a way of effectively adding the number of spin-ons to all orders, right? So basically one spin flip out of this state basically creates two spin-ons. If I have two spin flips, that basically creates four spin-ons, et cetera, et cetera. And in the ground state, what would be the nail state when I comprise this singlet state is, composed of a big superposition of those, but I start flipping spins out of that, and each spin flip gives me two more spin-ons. So it's adding all those states together and looking at what they contribute to the response function. And the green line, the Moeller ansatz, was basically a pretty good guess as to what the response function had to look like. That was based on a combination of matrix elements inferred from finite size diagonalization coupled with some rules and some extrapolation. And what you're looking at here, where it fails is actually toward the upper edge of the boundary. Okay, so it had a sharp cutoff in the Moeller ansatz. it doesn't quite go down the same way as a more sophisticated calculation.
Okay, thank you.
Zilka has a question.
Yeah, that question sort of goes back to the question that came before, Tim. So if you have a field-induced quantum critical point, you had a publication on cesium cobalt chloride, right?
Actually, that I'm not a co-author on that publication, but there is.
Okay, but maybe you know it. So my question was, I mean, there also the quantum Fisher information was measured, right?
Right.
And it
yes.
was found that it is minimum at the quantum critical point. So that was sort of a similar to this transverse Ising model, right? And I think wouldn't the expectation be that it is maximum at the quantum critical point?
Well, I don't want to comment on that without going and looking at the paper.
Okay. Okay. But expectation, isn't it that at a quantum critical point, or maybe only at certain quantum critical points, the quantum Fisher information could be maximized?
I think I have one possible answer, maybe just to interject. I think we know that, yeah, bipartite entanglement, I mean, in a way, this is indicating that quantum Fisher information is probing a slightly different kind of entanglement from the standard bipartite entanglement that we've obsessed over. So bipartite entanglement is indeed larger at 1D quantum critical points, but I don't think that has to be true for the multipartite, like the irreducible 3-particle entanglement and things like that. I don't think those are totally understood yet, actually. So I guess this would be saying that QFI behaves a little bit differently, as I understand it. So this is one possible answer. I don't know, maybe Steve has another.
But it would also depend on at which Q vector you look, because I think that was actually at the ordering wave vector. Then maybe it's not so surprising that it's larger in the ordered phase than anywhere else. Isn't it? I mean that. So you said.
Well, I would expect that. Yes, if I have a phase that's classically ordered, my intuition says the entanglement has to be less. But following up a little bit on what Joel said, it is true that these measures are not always universally applicable, right? They depend somewhat on the situation. As I said at the beginning, it's kind of like choosing an order parameter. They're not all of these entanglement witnesses are appropriate in all circumstances. And so I'll confess that I'm not that familiar, or not as familiar as I should be, with their Ising model. It is a much more, it turns out it's more complicated in that situation than it is for the isotropic system. So I don't want to say something that,
never mind, sorry.
It's totally uninformed.
Okay.
I'll go look into it, because it's an interesting point you raised.